page. Dr. Bevilacqua here. I wanted to go through and animate and talk through a little bit the intermolecular force review sheet, which is up on the website. And let's go ahead and just start with a few basic facts about these. And so the first thing is that they're all electrostatic in nature. In other words, electrostatic means they're due to interactions that have to do with electricity. And this is really fundamental to chemistry and to bonding. And the most important thing that you have to get out of this is that opposites attract. So if you have a plus charge and a minus charge, there's a favorable interaction. And likewise, if there are like charges, such as two positive charges or two negative charges, they repel. You're going to see that in the pictures and in the math. So let's go through the 5 different intermolecular forces that are drawn here. And they're written in order of weakest, London forces are the weakest, to strongest, which are ion-ion. So let's start up here. And the first thing that you'll know is that they have opposites being attracted. Here's a minus charge and here's a plus charge, just like up here, and they're attracted to each other. Okay, so another thing I want to mention is that when there is a favorable interaction, that is an attraction, the energy is always minus. We have to make it come out minus. And because there's no permanent charge on the London forces, we have to enforce that minus charge by putting a minus out in front of the equation. And you can see that there. All of these intermolecular forces involve two things coming together. So you'll always see two terms in the numerator. Here it's alpha 1 and alpha 2. That's the polarizability of species 1 and species 2. And the other thing that you'll see is that they depend inversely on distance. Because it's an inverse relationship, that means small r is big energy. And big R is small energy. So in other words, the two things have to get very close together in order to be attracted to each other. And the higher the power, the closer they have to get together. So in other words, for London forces, the two species that are interacting here, let's say two argon atoms, have to snug right up next to each other. Let's say to within less than a nanometer, even a few angstroms of each other. And if you're not familiar and real handy with the metric system, make sure you go back and review it and know a nanometer and know what an angstrom is. Okay, then another really important part of these is whether they're directional. These are not directional. They just take two argon atoms to come together. There could be one here, and there could be one there, or there could be one there, and the other one could be here. That works equally well. So there's no directionality to it. They're relatively weak, worth only about -2 kilojoules per mole. That number should mean something. At this point to you guys, you'll remember that delta H for separating 1 mole of water into the gas phase is about -40, and that covalent bonds can be upwards of 200 to 400 kilojoules per mole. All right, so let's move on. The next one, number 2, is permanent dipole, permanent dipole. And so are these directional? Yes, they are directional, and you can see that here. And so these guys are in a straight line. All right, and that's the most favorable way that they can be. If the orientation is random, they can still have an interaction, but it falls off as 1 over r to the 6, meaning they don't persist very long in space. These ones go as 1 over r cubed. They're worth a little bit more, about twice as favorable as the energy of the London forces. Again, there's no overall charge. The charge is neutral. They're just dipoles. And so we have to enforce the minus sign by putting a minus sign out in front. We have to enforce the fact that they're favorable and negative by putting a minus sign out in front. It's a pairwise interaction again. Pairwise means a pair between two things. One dipole and another dipole. All right, and so you can see again two factors being multiplied together in the numerator, just like two factors up here. There's a constant. We're not going to worry about what that constant is. And here's an example. so that you can know a permanent dipole when you see it. You see this particular example in CH3Cl, and there's a electronegativity difference between the carbon and the chlorine. Chlorine is much more electronegative. Make sure you know the periodic trends on electronegativity. It's highest in fluorine, and it decreases diagonally across the periodic table to cesium. So we know there's a positive charge left on the carbon, and there's a negative charge, partial negative charge on the chlorine. That's where we use these delta symbols. Make sure you can write a delta. There's also one, it wasn't shown explicitly, but of course it's the same delta plus as over there, and on this Cl a delta minus. It's minus because it's more electronegative. And so then we end up with a dipole here. There's a positive on this end, a minus on this end, and we end up with the same one with a positive here. And here's the opposites attracting each other, minus and positive. And of course, there's orientation to this and directionality, and they go in this direction. So for example, if I pretended that this one was going the other way, let's just pretend for a second, then the dipole would go in this direction, and then I'd have the two delta minuses next to each other, and that would be really unfavorable. So we would never write it the way I just did. Instead, we write it this way so that they line up in this fashion. All right, let's move on to hydrogen bonding. Extremely important in biology. The atom here must be nitrogen, oxygen, or fluorine. In biology, there's no fluorine naturally, so it's nitrogen or oxygen. And these are like permanent dipoles. You get charge separation because of the electronegativity difference. Oxygen is the second most electronegative atom in the periodic table, so it develops a delta minus. And you can see the orientation here is much like it was up there. Okay, and again, it's electrostatic. We have minus attracted to plus. Opposites attract, and minus next to plus. Opposites attract. Now, we have likes. We have two minuses, but notice that they're far away from each other. And because these interactions go as 1 over r, bigger differences means weaker. So there is repulsion. You don't get something for nothing, but the repulsion is further away, and so it contributes less. And there's covalent character to this part of the bond right here. And make sure you know these definitions. These are donors. This donates the hydrogen bond, and this is an acceptor. It accepts the hydrogen bond. It's optimal if these are linear, and like shown here in a straight line. These 3 points are on a straight line. If I were to take y, I'll draw it the wrong way, similar to how I illustrated it above, and I did this. This is a 90-degree angle, and it's not favorable. Why not? Well, it still has the two attractions, minus the plus, but there's this repulsion, and the repulsion's much closer here than it was here. So we don't draw it at a 90-degree angle. I'm going to delete it. And instead, it's optimal to be linear. And this is really important. This gives rise to shape in proteins and in DNA and RNA and all sorts of materials. Kevlar, bulletproof material, has its shape largely because of hydrogen bonding and directionality. Really important. Okay, moving on. Now we're getting stronger and stronger. We've got ion dipole. Okay, so here's an ion right there. Positive charge, that's the cation. Here's the anion. Notice that it's been cartooned bigger in general. Anions are bigger. They have more electrons than cations. And also, so that's the ion part. Let's go to the dipole part. Here's the dipole right here. This is water. Water, again, we're depicting water. HOH has a shape like that, a bent shape. And so we know that water is delta minus. And so is delta minus on the oxygen, so there's a delta minus right there. And so again, look, electrostatics, attractive interactions between the minus and the plus. And likewise, notice how the water is oriented here. It's oriented so the delta plus of the hydrogen from the water right there is near the minus. So again, we have favorable electrostatic interactions, just like in every other case. And also notice it's pairwise, 1, 2. Okay, and so again, pairwise, you see two terms in the numerator. The mu is the dipole, and that has to do with charge times distance. If I back up for 1 second all the way up here to 2, you also notice that the two terms being multiplied are mu, and those are charge times distance, charge, distance. And that mu is the same mu that's down here. And z is the absolute charge, magnitude of the charge here. So this guy would be, z would be -1. And on this one, z would be +1, like cartooned here. And you take the absolute value. So if it's minus, it becomes positive. This whole numerator is positive, yet we know the energy must be negative to be favorable, so we enforce that with a minus charge. And how favorable are these? Well, let's go back. London was -2. Permanent dipole was -4. Hydrogen bond about -20. These are quite strong, -120 per mole of sodium, okay, per 1 sodium. But notice that there are 4 waters depicted here, 1, 2, 3, 4, but there's actually 2 more. There's one in front and there's one behind the computer screen, so there's 6. And that's an octahedral arrangement. So those 6, because there's 6 waters, it's 1/6 the 120 value, or about -20 per mole of water. All right, last but not least, we've got ion-ion. We've got the cation here interacting with the anion. Notice the anion depicted as being bigger than the cation. This is really a whopper in energy, -500 for sodium chloride, and not surprisingly, if we go to magnesium sulfide, as depicted here, it goes as the product of the magnitude of the charge, z1 times z2. z1 is -1, z2 is +1. That naturally gives a minus sign, so there's no minus sign here. It comes out naturally from the product of these two. And in fact, if these were the same charge, plus and plus or minus and minus, it would naturally come out to be positive, which is repulsive, so that makes sense. And so sodium's +1, chloride -1, magnesium sulfide +2, magnesium +2, sulfide -2, and so it is really now here the product of the +2 and the -2 that gives rise to magnesium sulfide being 4 times larger in magnitude than sodium chloride. And that's where you see that these values differ by about 4-fold here, and that's because it's 2 times 2 rather than 1 times 1. Okay, and lastly, that's why if you go and look at the deviations of the Van Hoff factor from ideality as you concentrate solutions, you'll see that magnesium sulfide, or I think it was magnesium sulfate in the examples, deviated much more than sodium chloride. That's because these are attracted to each other almost 4 times more. Now the distance is a little bit bigger, but the effective distances are always small. Charge always trumps distance, and that's why these are more likely to ion pair in solution and give greater deviations in the Van Hoff factor. Lastly, let's talk about distance dependence. So you can see the distances are listed here as r to the -1, -2, -3, and -6. Where do those come from? They come from here. R to the 1 over r to the 6, which is r to the -6, 1 over r to the 3rd power, 1 over r squared, and 1 over r. Hydrogen bonding doesn't really have an r. We just know because of the covalent character that they need to get within, a typically pretty close. Not as small as a covalent bond, but almost as small. So you should know that these distances have to be, that distance is the distance between the what we call the heteroatoms, the x and the y, the ones without the h. All right, so returning back to the power on r. So you should be able to plot 1 over r. If you plot 1 over r, when as r gets smaller, and if this is -y, this equals -y, then what will happen is if this if this is y over here, then, not minus y, just y, then what will happen is r gets small, y will get big, but there's a minus sign, it'll send it down like that. All right. Now, if I put a power on here, then it gets smaller faster. So it does, it'll do something more like fall off really quick. So that's what you're seeing here. Dr. Showalter depicted this really nicely. Here's 1 over r to the 6th. Not much happens, but when it does happen, it falls off faster and down in here. But that doesn't matter because this distance is forbidden in here. Nuclei can only get so close, and then what happens is actually the electrons repel each other. It's forbidden by quantum mechanics. We'll talk about that in a few weeks, the Pauli exclusion principle, because otherwise if they get that close, then they might get the same quantum, the same 4 quantum numbers, which is prohibited. Okay, so in other words, when you look at these plots that are sketched out here for you, you should only look at this part. The part that's shaded, here is forbidden. So only look at this part. And what you can see is that the energy for 1 over r is lower than for 1 over r to the 6th. If I pick some distance r, you can see 1 over r goes to that value, but 1 over r to the 6th only goes down to this point right in here. So in other words, that's part of where ion, which goes as 1 over r, gets its bigger energy from, is the fact that this is down further, and this is not down as far for London. The constants come into effect as well. The other thing to notice is that, excuse me, is that at long r, this has gone to 0. Okay, London dispersions are gone, but ion persist out to long distances. So as a rule of thumb, again, these have to be within a few angstroms of each other to get London interactions, and these can go all the way out to even as far as 7 or 8 angstroms. It depends on the dielectric. And so there's some really nice examples in here that you can look at. In fact, over here it shows you how to really think about it. Just like I said, we don't even plot that part. And I'm just going to go down here and summarize for you. Here are the 5 interactions. There's London interactions, dipole-dipole, hydrogen bonding, dipole-ion, ion-ion. And what you can see is that the permanency of the charge increases. Here the charges are fully developed. Here they're not developed at all. They're only instantaneous. Here they're partially developed as dipoles. So the more developed they are, the bigger the energy. This is plotting energy. Energy is getting bigger in magnitude and more favorable, more negative. The other thing that's important is the distances. These persist to long distance. So n is going down. N is only 1 here. N is 6 up here. So these are big energy, and they go out long distances. And that leads these to have very strong attractions. If you have any questions, be sure to see us or see one of the LAs, and thanks for listening.